Okay, we're going to take a look at an informal proof of the Pythagorean Theorem. The Pythagorean Theorem is a famous theorem that will be used throughout much of high school mathematics. And we're going to start taking a look at it now. We're going to see several proofs of the theorem throughout this year and next year, and you're going to have plenty of practice using it before you actually have to do the formal proof of the theorem. But the first thing you need to know about the Pythagorean Theorem is what it states. And that is, if the lengths of the legs of a right triangle are a and b, and the length of the hypotenuse is c, then a squared plus b squared equals c squared. So given a right triangle ABC, with c being the vertex of the right angle, then the sides AC, which is right here, AC, and BC, which is right here, are called the legs of triangle ABC, and side A to B is called the hypotenuse of triangle ABC. One thing we want to point out is angle A actually corresponds to side A, and it's on the opposite. It's kind of like the remote side, if you want to call it that. If angle C is the right angle, which typically that's what it is, then the hypotenuse is the farthest side away from angle C, and that is lowercase c. And then B is indicating this angle here, which refers to lowercase b, the farthest side away from the angle. Now, A and B are interchangeable, but C is always usually referred to as the right angle, and C is the hypotenuse. So the first proof we're going to take a look at requires you to know some basic facts about geometry. And some of these we know, and some of them we really haven't investigated that much yet. All right, first one is congruent triangles have equal areas. We've taken a look at congruent triangles. We haven't really specifically talked about the areas, but if we have, it's all about mapping again. If you can map a triangle onto itself, then it has to have an equal area. The other thing is triangles can be considered congruent using the side angle side criterion, and that is abbreviated SAS. And we're specifically looking at all corresponding parts of congruent triangles are congruent. The last thing, which you should be familiar with, is the triangle sum theorem. More specifically, for right triangles, two angles that are not the right angle have a sum of 90 degrees, which would make sense. If you have 90 degrees for one of your angles, then the other two would have to equal the other 90, so that you can get to 180. So what we're going to use is a square within a square. Notice we have a big square, and we have the inside square. So we're going to refer to this as the outside square and the inside square. So the outside square has side lengths of a plus b. If we take a look at the top, b comes before a, but remember, commutative property of addition means that we typically put them in alphabetical order, so a plus b. The inside square has a side length of c, so this side length is represented by c. Our goal is to show that a squared plus b squared is going to be equal to c squared. So a squared plus b squared is going to be equal to c squared. We're going to compare the total area of the outside square with the parts it is comprised of. If you notice, this outside square has an inside square, but it also has 4 triangles. Here's 1 triangle, 2 triangles, 3, and 4. So looking at the outside square only, the square with side lengths of a plus b, what is the area? Well, the area of the outside square would be a plus b squared, because the square is the side times the side. But that can be also simplified to say a squared plus 2ab plus b squared. So let's take a look at how did we get from a plus b squared to a squared plus 2ab plus b squared. All right, so if we write this out, a plus b, oops, I need to switch over to my pen. All right, so a plus b squared means that I'm going to multiply a plus b times itself, a plus b. Well, when we do this, we have to do distributive property. And so I take a term from the first factor, multiply it by each term in the second factor, and then do the same thing with b. So I'm just going to draw some arrows here, some lines to show you what I'm doing. So I'm going to first multiply a times a. Well, that would be a squared. But then I also have to multiply a times b. And we're adding, so a times b is ab. Now I have to do the same thing with b. I have to take this and multiply it by this term. So b times a is the same as a times b. And I also have to multiply b times b, which is b squared. So now I have a squared plus ab plus ab plus b squared. Well, if you notice here, ab plus ab is how many ab's? Well, that would be 2. So I can simplify this as a squared plus 2ab plus b squared. And that is how the quantity of a plus b squared is equal to a squared plus 2ab plus b squared. Okay, let's go ahead and switch back to our arrow. If I can get it to do that. Where are you? There we go. Okay. Are the 4 triangles with side lengths A and B congruent? So A and B, these are side lengths. Are they congruent? If so, how do you know? Well, the answer is yes, they are congruent. And the reason they are is by the side angle side. What is the area of just one triangle? Well, if the area of a triangle is 1/2 times the height times the base, this would be the height of this triangle and this would be the base. So that would be 1/2 times AB, because A is our base and B is our height. Does each triangle have the same area? If so, what is the sum of all 4 of those areas? Well, if this is 1/2 AB and I have 4 of these, then they have the same area because they have the same side lengths. And the sum of all 4 triangles is 4 times 1/2 A times B. Well, 4 times 1/2 is 2. So we can simplify this to 2AB. Alright, so we called this entire figure a square within a square, but we want to make sure that the figure inside of here is really a square. To do so, we need to look at the angles of the triangles. Notice how we have some blue marks here indicating the congruent angles, and we also have some red marks. So first of all, what do we know about corresponding angles of congruent triangles? Well, corresponding angles of congruent triangles are also congruent and they are equal in measure. And again, if we wanted to really go back and prove it, we could map each one of these by a rotation or a translation and a rotation. So we have the blue angles correspond with each of these, and the red angles correspond and are congruent with each of these. So we know that the angles marked by red arcs are equal in measure, and the angles marked by the blue arcs in a line are also equal in measure. What do we know about the sum of interior angles of a triangle? You should be able to answer that. Well, they are 180 degrees. What is the sum of the two interior angles of a right triangle? So if we take one of these triangles, I have a 90-degree angle and I have these two angles. What do I know about adding these two angles? Well, they're going to be 90 degrees. And why? Because I know that all three angles have to equal 180, and if one is already 90, then the other two have to add up to be 90. Now let's just take a look at one side. We'll take the top side here. Okay? We have an angle with a red arc. We have an angle with a blue arc. In between the red and the blue arc here, we have another angle. We don't know the measure of this angle. However, if I add all three of these angles up, they need to equal a straight angle, which is also the side of the big square, the outside square. What must the unknown angle measure be? And how do we know that? Well, it's got to be 90 degrees. Because if we have a red arc and the blue arc has to have a sum of 90, then the remaining arc also has to have a sum of 90 degrees. Because a straight angle, or angles on a line, have to equal 180 degrees. So that means the figure with the side length of C must be a square, because it has four equal sides, C, 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 and C, and it has four 90-degree angles. This is 90, this would be 90, this one would be 90, and this one. So, if that's the case, then what is the area of the inside square? Well, if it's side times side, then that means it has to be C squared. So let's go back to our goal. We want to show that A squared plus B squared equals C squared. What we're going to need to do is compare the total area of the outside square, so this whole area. We want to compare that to the sum of its parts. So the parts of this area is 4 triangles and a smaller square. Do we have everything we need to accomplish this? Absolutely. We know the area of the outside square. That was at the beginning when we did the quantity of A plus B squared. And then we factored it out and simplified it to A squared plus 2AB plus B squared. We also know the area of the 4 triangles. That was 4 times 1/2 AB, which can be simplified to 2AB, and we know the area of the inside square, which is C squared. So to end the proof, if we want the total area of the outside square, we need to add the area of the 4 triangles plus the area of the inside square. Well, here is our area of the outside square. It is equal to the area of the 4 triangles plus the area of the inside square. Notice what we have on both sides of the equation. We have this 2AB, which can be subtracted. So if I have a 2AB, I can subtract a 2AB from here, and I'm going to do the same thing to the right side of the equation. When we do that, that's going to leave me with an A squared, a B squared, and over here a C squared. Hence, A squared plus B squared equals C squared, and that's the end of the proof. Take a look at example 1, read through it. And then also take a look at example 2 in your classwork packet, and then continue on with the video. So specifically taking a look at example 2, based on our work in the last example, what should we do to find the length of the hypotenuse? Well, you're going to use the Pythagorean Theorem and replace the b with 3 and 7. Or I'm sorry, replace a and b with 3 and 7. So doing that, now we have 3 squared plus 7 squared equals c squared. 3 squared is 9. 7 squared is 49. And when we simplify 9 and 49, we get 58. And that is equal to c squared. If you know how to figure out what number times itself produces 58, then you could go ahead and figure out what c is. But for right now, we're going to leave it as 58 is equal to c squared. All right, go ahead and complete exercises 1 through 5 in the class work packet. And then go ahead and come back to the video to see the answers. So here are the answers, 1 and 2. And you can stop and start as needed. I'm going to keep going. Here's answers for 3 and 4. And the answer for number 5. Notice the work that is being shown for each of these. It is not just the answer, but it starts with the Pythagorean Theorem, and then the substitution, the simplifying, and then the final answer. The equal signs are always lined up underneath each other so that it's easy to follow from one step to the other. That is the work that you should show to answer these questions. So to summarize, we were shown a proof for the Pythagorean Theorem that required us to find the area of 4 congruent triangles and 2 squares. We learned that right triangles have a sides A and B, known as legs, and a side C, known as the hypotenuse. And last, we know that for right triangles, a squared plus b squared is equal to c squared. All right, we'll see you in class.